Hi students. Many times in our daily life we talk about pure substances, isn't it? We talk about pure salt, pure milk, pure butter. You know, is this thing pure? Is this oil pure? We talk in such terms. But what is pure for a scientist? You can have pure milk, but is that milk pure for a scientist? You can have pure salt, but is it pure for a scientist? And what about this butter? If the packet says pure butter, does that mean that a scientist will also find, that this butter is pure? Not really. In fact, all these substances that we use in our daily life are mixtures. In this chapter, we're going to learn the meaning of a mixture and, different types of mixtures. We're also going to learn how to distinguish between a pure substance and a mixture. Understood? For a scientist, what does the word pure mean? And if something is not pure, what does the word mixture mean? We learn about pure substances and mixtures in detail in this chapter. The meaning of a mixture. So let's proceed. First of all, before we understand mixtures, let's understand what the word pure means. Simply put, the word pure means that, a pure substance will consist of a single type of particles. Isn't it? So for example, this substance, whose particles you can see moving on your screen, it's a pure substance. That is because this substance consists of only one type of blue particles. Isn't it? You can see that on your screen. There are no other types of particles. So all pure substances contain only one single type of particles. If you take water for example, which is a pure substance, water always consists of water particles. Isn't it? Like no matter what physical process you make water undergo, it will always consist of only water particles. So really pure substances contain only one single type of particles. This is one important characteristic of a pure substance. Another important characteristic is that pure substances cannot be broken down into other substances by means of physical processes. So for example, if you filter a pure substance like this, even then you'll still obtain the same pure substance. If you break a pure substance like this, something like this, you will still obtain different pieces and different particles of the same pure substance. Pure substances cannot be changed into something else by physical processes. Physical processes, when I say that, I mean breaking, dissolving, cooling, vaporization, using your hands. You just cannot break a pure substance into another substance. Why? Because it's pure, isn't it? So these are the two important characteristics of pure substances. One, that they contain the same kind of particles, and two, you cannot break them to get different other substances. In fact, we can now define a pure substance. A pure substance is a form of matter that consists of only one kind of particles. It cannot be separated into other substances by physical processes. Understood? So we've summed up both these points in this definition. Let's now take a look at some substances which we see in our daily life. Take a look at this. Water. Water is a pure substance, isn't it? It contains the same kind of particles, and no matter what physical process water undergoes, it still remains water. Sugar. All sugar contains the same sugar particles, isn't it? No matter what you do, you cannot break sugar and get, say, iron or gold or anything else. Similarly, gold itself is a pure substance. As you can see, all these substances are pure because they contain the same kind of particles, and no matter what physical process they undergo, they will not change, like they'll not give some other substance. In fact, let's take a detailed look at water. If these blue particles you see are water particles, in that case clearly, no matter what sample of water you take, no matter what quantity you take, water will always have water particles and no other type of particles. Now, vaporization is a physical process. When you heat water, water turns into steam. But steam is still H2O, isn't it? Steam is also still water. So, no matter how much you heat water, water remains water. Similarly, if you filter water, what will happen? the water that falls into the filter will be the water that will come out of the filter. So filtering also does not change water. Similarly, if you cool water, water will become ice. Water will become ice like this. However, it remains water on cooling, because ice, water, steam, as we learnt in the previous chapter, they are all just three forms of water. Water hasn't changed. So this helps us conclude that water is a pure substance. On the other hand, look at milk. Is milk a pure substance? Scientists have, analyzed milk, and using different processes like filtration, a special process called crystallization, and many other processes, they have concluded that milk is not a pure substance. In fact, milk contains enzymes, vitamins, pigments, salts, proteins, and sugar. Again, all these are complicated terms, which we haven't yet learnt about, enzymes, vitamins, pigments and all. But the point here is that milk can be broken down into these substances. So milk, if you carry out many physical processes, like if you boil it and then if you carry out a special process called pasteurization, many things happen. And milk can actually be separated into all these components. Understood? So as you can see, milk is a mixture. It's not a pure substance. Similarly, take your soft drink cans. Are soft drinks pure? They aren't. Using special physical processes, you can actually separate soft drinks into carbon dioxide, water, a substance called caffeine, and different flavor chemicals. So as you can see, it does not contain the same kind of particles. Carbon dioxide is a pure substance, water is a pure substance. But as you can see, carbon dioxide and water and caffeine and flavor chemicals, so soft drinks contain different types of particles. So soft drinks can't be pure, isn't it? Similarly, they can be broken down into these different substances by using physical processes, so they're not pure. Let's take another example. What do you think about salt water? It's not pure. And you can easily find out why salt water is not pure. It contains two types of particles. It has sodium chloride particles and water particles, isn't it? But we had just said that a pure substance contains only one kind of particles. So sodium chloride is pure, water is pure, but salt water is not a pure substance. Understood? It's a mixture. Here you can see, salt water. If you imagine that the blue particles are water, in that case the yellow particles represent sodium chloride. So you can see there are two types of particles. Again, when you heat salt water, the water evaporates, leaving only salt. And that tells us that this mixture can easily be separated by heating, a physical process. Isn't it? So there you go. Now that we've studied, so much about a mixture and a pure substance, let's try to, define a mixture. What exactly is a mixture and what are the different types of mixtures? A sample of matter that is formed due to the physical combination of two or more pure substances in varied proportions is called a mixture. So now this definition might seem very complicated to you, but actually what it says is that when you take more than one pure substance and when you combine these pure substances, you get a mixture. As simple as that. The reason a mixture has different types of particles is because it has different pure substances in it. And you can easily separate a mixture into the different pure substances by using physical processes. Mixtures, when they undergo physical processes, give pure substances, isn't it? We just saw, for example, that sodium chloride solution, when you heat it, heating being a physical process, you get pure substances, water and sodium chloride. Some other physical processes that we can use are cooling, breaking, dissolving, filtering, so many things. For example, if you have a mixture of, say, sodium chloride and iron filings, of course, you can, add water to the mixture. The sodium chloride will dissolve in the water and the iron filings will be left behind, isn't it? So you can say that by dissolving also mixtures can be separated to pure substances. Sometimes they can be separated into pure substances by breaking. So whenever you use physical processes, mixtures get separated. Let's look at some more examples of mixtures. Soil is one mixture, that we keep on seeing every day. Why do we say that soil is a mixture? See, that's simply because you can take soil and you can separate it into clay and sand and stones and many other parts of soil. So soil is not one single pure substance. It contains many other pure substances. Again, sugar water is another example of a mixture, isn't it? After all, it contains two pure substances, sugar and water. Another example of a mixture is copper sulfate solution. Of course, it's a mixture because it contains two substances, copper sulfate and water, isn't it? Again, you can heat copper sulfate, and when you heat copper sulfate remains and water evaporates. So you can say that this mixture can be separated by a physical process. So you just saw, that pure substances contain one type of particles and they cannot be broken down into other substances by physical processes. Mixtures consist of one or more pure substances and they can be easily broken down into their constituent substances. Understood? Now that we've studied about pure substances and mixtures, let's take a look at the different types of mixtures. You see, there are different types of mixtures based on the properties of mixtures. One nice way to classify mixtures is, on the basis of the uniformity of the mixture. What does that mean? I'll explain in a moment. Mixtures can be classified as homogeneous mixtures and heterogeneous mixtures based on how uniform or non-uniform the mixture is. A homogeneous mixture is one which has a uniform composition throughout. Now what does that mean? So what a homogeneous mixture basically means is, that its components cannot be distinguished. Its composition is the same throughout. Let's take the example of salt water, which is a homogeneous mixture. If you take this part of salt water here, the upper part, it will have the same amount of salt and the same amount of water. If you take the bottommost part of salt water, it will still have the same amount of salt and the same amount of water, isn't it? So basically what you can say is that all the constituents of the mixture are distributed uniformly throughout the mixture, isn't it? You cannot say that one part of the salt water has more salt and less water and another part of the salt water has more salt and less water. So all the components of the mixture in a homogeneous mixture are uniformly spread out. Understood? Take copper sulfate solution. If you take again one spoonful of copper sulfate solution from the top and from the bottom, you'll see that it has the same amount of copper sulfate and water. In fact, every part of the copper sulfate solution has the same amount of copper sulfate and water. So a uniformly spread out mixture is called a homogeneous mixture. You cannot of course distinguish the components of a homogeneous mixture. If you look at a copper sulfate solution, you cannot say, oh, this is copper sulfate and this is water. Why? Because copper sulfate and water are not separate in the mixture. They're so spread out in each other that the concentration of copper sulfate and water is the same throughout the mixture. You cannot see separate copper sulfate crystals and separate water crystals in the mixture. So did you understand what a homogeneous mixture is? Basically a uniform mixture, in which everything is spread out uniformly is a homogeneous mixture. On the other hand, a mixture which has physically distinct parts and a non-uniform composition is called a heterogeneous mixture. Did you understand what this means? A heterogeneous mixture is one which has different components in different concentrations here and different concentrations there. So you can easily make out, okay, there is this component in this mixture, there is this component in this mixture. Take a look at oil and water mixtures. When you mix oil and water, oil floats above the water. So clearly the concentration is not uniform, isn't it? If you look at the bottom of this glass, then there will be hardly any oil there, isn't it? But if you look at the top of the glass, there will be a lot of oil there. So mixtures which are not uniformly distributed, in which there are different concentrations of components here, there and there and there, those are called heterogeneous mixtures. In a heterogeneous mixture, you can easily make out the components. You can easily say, okay, this is oil and this is water. If you remember the copper sulfate solution that we just saw, you cannot make out that this is copper sulfate and this is water. Everywhere there's just a mixture of copper sulfate and water. In this case, however, you can make out, that oil is on the top, water is on the bottom. Similarly, if you look at a sulfur and salt mixture, the yellow powder you see here is sulfur and the white powder you see here is common salt. Now clearly, this is a heterogeneous mixture. Why? That is because, the concentration of salt and sulfur is not the same everywhere. It's not a uniform distribution of salt and sulfur. You can see that there's a lot of sulfur in the middle here, but at the borders you can see that there's a lot of salt also. So you can clearly make out, okay, this is salt and this is sulfur, isn't it? On the other hand, if you look at a sugar solution, you cannot make out, you cannot say this is sugar and this is water. Everywhere there's sugar, water. So such non-uniform mixtures are called heterogeneous mixtures. Here's a nice, balance that tells you more about homogeneous and heterogeneous mixtures. Basically, homogeneous mixtures have a uniform composition. Heterogeneous mixtures don't have a uniform composition. Say salt water, homogeneous because it's uniform salt water everywhere. Salt and iron filings, non-uniform because there'll be more salt somewhere, there'll be more iron filings somewhere. In a homogeneous mixture, you cannot see and differentiate the components, isn't it? But in a heterogeneous mixture, you can easily differentiate the components because some components are more in some positions, some other components are more in some other positions. So you can easily say, okay, this component is here and this component is here. Understood? Salt is here and iron filings are here. But here you cannot say sugar is here or water is here. So that's the difference between homogeneous and heterogeneous mixtures. Understood? Well, this was one type of mixtures. There are also some other interesting type of mixtures. You can classify mixtures, based on the particle size of the mixing pure substances. Understood? So based on the particle size of the pure substances, which mix to form a mixture, you can again classify mixtures as solutions, colloidal solutions, and suspensions. Earlier we had classified mixtures on the basis of whether they are uniformly spread out throughout or not. Now we are classifying mixtures on a different basis. We are classifying them according to particle size. We are classifying them as a solution, colloidal solution, and suspension. A solution is basically, a mixture of particles which have a size less than 10 raised to minus 9 meters. Understood? Salt water is a solution. Both salt particles and water particles have a size less than 10 raised to minus 9 meters. Copper sulfate solution is again a solution because, even in the case of copper sulfate, the particles are less than 10 raised to minus 9 meters in size. Understood? So, we will learn in detail about solutions, colloidal solutions and suspensions in the chapters to come. But for now, all you have to remember is that a solution is a mixture in which the size of the particles is less than 10 raised to minus 9 meters. A colloidal solution is a mixture in which the size of the particles varies from 10 raised to minus 9 to 10 raised to minus 7 meters. Understood? So you can say that colloidal solution consists of pure substances which have slightly larger particle sizes compared to only solutions. Ink and water is a colloidal solution because the particles of ink, have a size between 10 raised to minus 9 to 10 raised to minus 7 meters. Milk and water is again a colloidal solution because again the particles of milk have a size ranging from 10 raised to minus 9 to 10 raised to minus 7 meters. Understood? So when you dissolve, things which have particle sizes greater than 10 raised to minus 9 meters and less than 10 raised to minus 7 meters, that's a colloidal solution. Again, we learn in detail about colloidal solution in the next chapter. For now, you should just remember about the particle size. The third type of mixture based on particle size is a suspension. In case of a suspension, the particles are quite large. The the particle size is greater than 10 raised to minus 7 meters. Now you might say that even 10 raised to minus 7 is quite a tiny amount, but still it's large enough for us to classify substances into a completely different category of mixtures. Chalk powder in water forms a suspension. Similarly, sand in water forms a suspension. So you can see that suspensions are mixtures in which the particle size is greater than 10 raised to minus 7 meters. Now you might say particle size and all is fine, but physically what exactly is a solution, colloidal solution or suspension? Well, a solution is basically a mixture in which the particles completely dissolve in water, or in which the particles completely dissolve in another substance. A colloidal solution is a mixture in which the particles dissolve, but not all of them dissolve. In case of a suspension, the particles don't dissolve only in the solvent. They just float around, they sink, but they won't dissolve. For example, sand in water is a suspension. Sand doesn't dissolve in water. Similarly, ink in water is a colloid. Ink just about dissolves in water. Sugar in water is a solution, and sugar dissolves perfectly in water. So more or less, you can understand a solution, colloidal solution and suspension by thinking that in solutions particles dissolve well, and in suspensions they don't dissolve at all. We'll of course learn more about all these three concepts in the next chapter. For now, we've learnt enough about mixtures and we've learnt about pure substances. So let's solve some problems that will clear our concepts related to pure substances and mixtures. Which of the following is or are pure substances? Air, water, milk and gold. Well, what do you think? Let's take a look at all these substances. Air. Air contains oxygen, nitrogen and carbon dioxide. You have already learnt about that earlier, isn't it? So clearly it can't be a pure substance. The reason is that a pure substance contains only one kind of particles, but air has oxygen particles, nitrogen particles and carbon dioxide particles. Water, however, is pure. That's because water has only one kind of particles, isn't it? Milk, as we just discussed, has enzymes, vitamins, sugar, pigments and whatnot. Clearly, milk cannot be a pure substance, isn't it? Because if it was a pure substance, it would contain only one kind of particles, but it has enzyme particles, sugar particles and so many other particles. Gold is a pure substance because gold contains only one kind of particle, isn't it? Again, you can also not separate out gold to give different substances. You cannot break gold and get, say, iron or silver, isn't it? You cannot separate gold into other substances by physical means. So there you go. Gold and water are the pure substances mentioned in the list. Water, gold. Let's now move on to the next problem. Give 4 examples of physical processes by which mixtures can be purified. Well, we learnt of a lot of physical processes just now. Well, there is filtering, isn't it? If you have a mixture containing sand and water, you can just filter out the water and sand will remain. You can break to purify a substance. If you have a mixture containing sulfur and salt, which is tightly held together in the form of a rock, you can break the rock to get salt and sulfur separately. Cooling is another option. If you have 2 substances with different freezing points, you can cool the substances, and then the one with the higher freezing point will freeze first, isn't it? And the other substance will still remain like a liquid. So you can separate mixtures using cooling also. Similarly, hand picking can help you separate mixtures. You must have seen that rice is sometimes purified by taking out all the stones and all the bad particles from the rice, so that it can be cooked, isn't it? You hand pick all the bad particles from rice. So basically that's a mixture, and rice is separated from what's not rice by means of hand picking. So there you go. These are 4 physical processes by which you can separate mixtures. There are of course many others, like say vaporization, dissolving, so many other processes. Here's yet another example problem. Why is a gas-gas mixture always homogeneous? Did you know that? You see, what happens is that in case of a gas-gas mixture, the particles of a gas always, spread out and occupy all the space available. Isn't it? We had learnt about that in the previous chapters. We had learnt that gases spread out and occupy all the space available to them. So if you have a box which contains two gases, both the gases will spread out and occupy all the space available to them. Isn't it? And therefore, after some time, the concentration of both the gases everywhere will be one and the same, because the gas molecules will move about everywhere and occupy all the space available. And therefore, if you have a mixture of 2 gases, 3 gases, 5 gases, however many gases, the mixture will always be homogeneous. A homogeneous mixture is one in which the concentration is the same everywhere. The mixture is uniformly spread out. All gases spread out such that their concentration is same everywhere. If you have chlorine in a box, the concentration of chlorine everywhere in the box will be the same. Now if you add oxygen and nitrogen also to this chlorine, then the concentration of oxygen, nitrogen and chlorine will also be the same everywhere. So because gases occupy all the volume available and because they diffuse until the concentration is the same everywhere, all gas mixtures are homogeneous. Understood? So that was the answer to this problem. So solving all these problems will help us clear our concepts related to mixtures and pure substances. Here's the last problem of this chapter. Can you solve it? Give examples of 2 solutions, 2 colloids and 2 suspensions. You see, we discussed solutions, colloids and suspensions. So what are the examples? 2 examples of solutions are salt water and copper sulfate in water. Isn't it? After all, we just discussed that in case of salt water, copper sulfate in water, or in case of mixtures where the particles dissolve completely in water, we get a solution. 2 examples of colloids are milk and water and ink and water. The particle size of milk and ink ranges from 10 raised to -9 to 10 raised to -7 meters. Suspensions are chalk and water and wheat flour and water. Understood? So if you take some wheat flour, the one you use to make chapatis and rotis, and if you dissolve it in water, it won't dissolve. It will settle down. In a suspension, the particles don't dissolve, they just settle down because the particle size is greater than 10 raised to -7 meters. Understood? So there you go. We have now studied in detail about different types of mixtures and how mixtures are different from pure substances. We've considered different examples of mixtures and pure substances. And so that brings us to the end of this chapter. Let's now move on to the next one.